Hi, my name is Ahmed Nasser. I'm a PhD student in nuclear engineering at École Polytechnique de Montréal. Today, I am going to talk about the first validation of the ELECTR model in NJOY. So, Boltzmann Fokker-Planck solvers start deployment in clinical routine as an alternative to Fermi-Higgs semi-empirical models and Monte Carlo code's drawbacks. Today, there is only one solver, Acuros, a rewrite of the US Los Alamos Attila SN solver. Multigroup cross-sections are from the 1989 US Sandia National Lab CEPICS code. The feasibility study was proposed in 2008. The validation certification work continued from 2008 until today. There are three limitations to this work. First, the CEPICS Acuros chain is not an open source chain. Acuros is limited to photon beams. And finally, CEPICS has only one version, never been upgraded or validated for electron beams. In this work, we present the first validation of the ELECTR Dragon chain as an open source alternative for electron beams. We will start with the validation methodology, then we will present the results in radio-oncology, followed by a quick experimental verification to end up with a meta-analysis for the entire periodic table. So the Boltzmann Fokker-Planck equation is a conservation balance that says that the rate of particles production is equal to the rate of particle streaming plus their absorption rate. The particularity is that the Boltzmann operator is separated into a catastrophic and a soft component. The soft component is for small angle scattering and small energy loss. Here we have the development in spherical harmonics of the Boltzmann operator for catastrophic collisions, and the first order Fokker-Planck operator for soft collisions. In our previous presentations, we explained how catastrophic transfer matrices are obtained and how soft stopping powers are calculated. We propose a validation of the NJOY Dragon chain against Geon4 on a set of an increasing complexity benchmarks. The first benchmark is a homogeneous water benchmark. This benchmark is of clinical interest for both daily calibration verification and treatment planning. The second one is the Rogers and Mohan benchmark. We have a first slab of water, followed by bone, lung, and the last water slab. This introduces the first level of complexity with high and low density thin tissues. Our goal here is to study the boundary crossing effect. The third benchmark is a typical breast intraoperative electron radiation therapy. We have a first cancer tissue to be radiated, followed by an aluminum and steel slabs that should guarantee the protection of an organ at risk. Here, the breast. We are then combining within patient low Z tissues and high Z materials. The last medical study case is the highly heterogeneous NJOY benchmark, 11 slabs containing bone, adipose, muscle, and lung tissues. A gradual increase in the beam energy from 1 to 20 mega electron volt is studied to challenge Legendre anisotropy, SN order, deterministic transport correction, and groups number. Here, our goal is to demonstrate the performance of the ELECTR kernel architecture and to highlight, if any, the limits of the state-of-the-art multigroup cross-section models. ELECTR can both work with CEPICS feed function or ENDF1s. We limit this presentation to the CEPICS mode in ELECTR. Reducing the CPU time is not of interest in this study. So quite conservative parameters are selected for the Dragon 5 scheme, 300 groups, S48 order, and 500 elements. For the Geon4 reference scheme, 15 million of primary events are considered for 0.2% standard deviation in every material. We use the Livermore physics-less constructor. Transport cutoff and secondary production threshold are both fixed to 1 kilo electron volt. Fluorescence and Bremsstrahlung photons are produced and eliminated at the point of birth. Here we have unidirectional and monoenergetic electron beams incident on water phantom. As E increase, build-up spreads, and higher PL orders were required. P9 until 6 MeV, P10 until 9 MeV, and P12 between 15 and 20 MeV. The insert shows the relative Boltzmann Fokker-Planck deviation with respect to the Monte Carlo scheme. The average Dragon giant error in absolute value over all space is of 0.4% at low energy and 0.5% at higher energy. For all beams examined, 100% of the water voxels satisfy the 2% American Association of Physics of physicist in medicine AAPM accuracy criterion. Now we use the same beams on the benchmark of Rogers and Mohan. Legendre requirements are the same as those of water. At 9 MeV, the mean Boltzmann-Fokker-Planck Monte Carlo error is of 0.8% for the first water slab, 0.5% for the bone slab, 0.7% for the lung tissue, and 0.5% for the last water slab. Overall, 98.2% and 98.4% of the Rogers and Mohan voxels satisfy the AAPM 2% criterion, respectively at 1 and 15 megaelectronvolt. It's clear that in some voxels, we have a loss of agreement. This is mainly caused by the bone interface. Here we zoom on and around the bone slab. Solid lines, Dragon 5, while circles, Geon 4. We see that the way Geon 4 manages this discontinuity is ambiguous. Dragon 5 predicted dose at the bone's interface is much more physical. Failures only concern the exact bone's interface. This jump behavior can be corrected either by forcing the electron step size not to exceed 25% of the voxel thickness in Geon 4, or 2, by optimizing the step size of the condensed history algorithm in Geon 4. If we disregard the bone interface discontinuity, 99.8% of the Rogers and Mohan voxels satisfy the AAPM criterion, all beams combined. Now we study this case of the surgical Mobitron benchmark: cancer, aluminium, steel, and breast. For the 9 MeV beam, the average Boltzmann-Fokker-Planck Monte Carlo deviation is of 0.6% for the cancer tissue, 0.98% for the aluminium slab, and 0.0% in both steel slab and breast tissue. The 0.0% of difference here means that a complete attenuation of the beam was achieved in the aluminium slab for both codes, which means that the organ at risk was protected. The Rogers and Mohan bone interface anomaly disappears at the aluminium interface. We study here the highly heterogeneous NJOY benchmark. The average Dragon-Geant relative error is of 0.5% to 0.6% as a maximum in bone, muscle, adipose, and lung voxels. For the entire benchmark, a minimum of 99.2% of voxels satisfy the AAPM 2% criterion. We have here 3 slabs of bone, 3 of adipose, 3 of muscle, and 1 of lung. However, answer shows that errors at the bone interface are lower than those of Rogers and Mohan. This can be explained by errors counterbalancing effect from the neighboring slabs backscattering, given that we go from 4 slabs in the previous case of Rogers and Mohan to 11 slabs in the present case of NJOY. Now we show Dragon 5 energy deposition profiles compared to Lockwood's experimental data and XNRC on 4 benchmarks. From the left to the right, aluminium, gold, aluminium, B, carbon, gold, carbon, C, carbon, copper, carbon, and D, homogeneous uranium slab. 2 Dragon 5 computational schemes are studied, the first with the legacy CEPIX BFP multigroup library, and the second with our model. 3 observations can be made. First, the CEPIX fit function in ELECTR are equivalent to the CEPIX to the CEPIX BFP code. This says that the ELECTR kernel architecture is reliable. Second, the Dragon 5 Lockwood difference is lower than the experimental data precision, which is about 2%, and this for 98% of the voxels, all benchmarks included. Third, the Dragon XNRC agreement is lower than the precision on the cross-section, and this for 100% of the voxels. We now answer the question, what would be the limit of the CEPIX mode in ELECTR for beams from 1 to 20 megaelectronvolt? We propose an electron irradiation of successive homogeneous slabs covering the entire periodic table. These figures show Dragon-Geant relative error in energy deposition profiles as a function of materials depth from lithium up to californium. All the energy deposits are followed until a complete beams attenuation. Because we are out of time, we propose to condense all these subplots in one summary figure. We show here for 3 beams the percentage of voxels satisfying a 2% in blue and 2.5% in red accuracy criterion between Geon 4 and Dragon 5. for each atom. So we can easily identify three classes of interest. First one, apart from exceptions, the 2% criterion is respected for all voxels, all beams combined, from hydrogen up to cerium, atomic number 58. From atomic number 59, paracetaminium, we observe a systematic Monte Carlo Boltzmann focal Planck deviation triggered around Dmax, the depth of the maximum dose. The latter error both increase and expands with Z, independently of the beam's energy. It increased slowly from atomic number 59, error of 2.3%, to uranium, where it stagnates at around 4.6%. From neptunium, we observe a third class for which the failure is total and considerable, higher than 20%. So we therefore retain that the CPXS fit function in ELECTR are acceptable from hydrogen to cerium, except pure gas media. So to summarize, we proposed NJOY ELECTR Dragon Chain as an open source Boltzmann focal Planck alternative to Fermi-X semi-empirical models, but also Monte Carlo codes and Accurate solver. Validation work was proposed on a set of an increasing complexity benchmarks. We used unidirectional and monoenergetic beams covering the entire radiotherapy and radiosurgery energy spectrum. We reported performance and effects of the CPXS mode in ELECTR for the entire periodic table. Those distributions were compared to those of Geon4, XNRC, and Lockwood's measurement. We observed high accuracy for radiooncology benchmarks within cross-section accuracy and experimental data precision. Our next step is to use ENDF fit function and to optimize the Boltzmann focal Planck computational scheme. Thank you for your attention.